So I'm Paul Birnbaum. I assume you know my wife, Nita. Anyway, I work here in El Segundo at the Boeing company. It used to be Hughes Aircraft Company when I first joined. And I work with satellites, and I've been doing it pretty much for 40 years. So I'll get a little more into that as we go on. And here's some pictures of some of those satellites that I've worked on, all these kinds of satellites. Actually, and in the background here on the right, you can see this is kind of Boeing companies right here. We are literally across the street from the airport. So my building I sit in is actually literally right across the street from the airport. So a few years ago when the shuttle came running around and flying around LA, I watched it land right at the airport there. It was cool. Anyway, um, there's just a picture of me and my friends at Cape Canaveral when I was there one time working there, and just showing you that besides an engineer, I do have a lot of other interests and things I like to do, running, play guitar. So life isn't all about engineering, but it makes the fact that I can engineer makes me able to do all these other things I like to do. Anyway, how did I get here? So when I went to school, I actually wanted to major in physics. Well, when I was a kid, I always loved nature and science and astronomy and stuff. And then I went to college. I actually wanted to study astrophysics. Like I said, I liked astronomy, but I ended up getting a degree in math. And I discovered I love computers and engineering. So, I studied math for a while, and then I took some programming courses, and I said, wow, this is really a lot of fun. And it was a time a while ago before they had, when I went to school, they didn't have all the computing majors and stuff like that. In fact, it wasn't even a major at my college. You had to get it. In fact, the first programming course was taken in the business department. So we didn't have a computer science department or computer engineering department when I was there, but I found I loved that. So when I got out of college, I started doing that. I worked for the power company in New York called Con Ed, and I ran all their computer systems and helped their engineers write computer programs. And I moved out here to California and worked for another software company called Logicon. And that's where I really got into working on microprocessors and things like that. I worked on software that runs. So if you know the helicopters that fly now with like all sorts of sensors, I worked on one of the sensors on one of the helicopters and was working on the software to control that sensor. And then after that, I decided I want to get into a bigger company. And so I heard about Hughes Aircraft, and they were doing some really exciting stuff. And so I went there, and that was 40 years ago. So I've been there since 40 years. It got bought out by General Motors and then Boeing. And so now we're called the Boeing Company. But essentially, I've been at the same place for 40 years. And like my chart says, I've ended up having like 6 different careers, even though I've stayed at the same place. So like I said, I started out just being a software engineer, writing code. Eventually, I became like a software system designer and project manager. I worked on big systems where we hooked a lot of computers together, and we were processing satellite data and figuring out how to put it all together and do some advanced computing stuff that nobody had done before at the time, which now seems pretty simple with all the stuff we had, but at that time, computers were pretty primitive. And in that part of that was I started working on, like I said, I was doing processing of data from satellites. So I said, well, I really want to work on satellites. So I moved to another part of the company, all in El Segundo, worked in all these different blocks. I'm always in a different building. My wife can never keep track of me where I'm at, which is a good thing. I can hide from her. Anyway, I decided I want to be an oral analyst. And then I worked on mission director and senior flight engineer. So those are all the guys. So people asked me for years what I've done. And I tell them I fly satellites. And that's all the kind of jobs you do to fly a satellite. I'll get into some of that later, but really I did all the maneuver planning analysis and how to put a satellite, get it off the ground from Earth and get it to wherever it's supposed to go out in space. And it's a complicated thing, and you have to do a lot of planning. And then I actually got to do it too. So not only did I do the analysis and planning beforehand, but I actually sat on console and did all that stuff. So like if you watch movies and you see guys with headsets and consoles, I was one of those guys, and I did that for about 25 years. I don't do that so much anymore, but it was a lot of fun. I loved it. And in fact, when I retire, they'll probably want me to come back and do it some more because I was so good at it. But anyway, I did that for a long time. And then I also got to work on lots of other things. And while I was doing all that, I also went back for more education. So one of the nice things about a lot of these companies is they'll pay for you to go to school. So I got my graduate degree at USC in electrical engineering. And I also, like I said, since I changed jobs and stopped doing so much programming and wanted to work on satellites, I went and took astronautics courses at USC again. So I almost have two master's degrees, but I never kind of officially got a second one, but I took enough courses for a second master degree. So I got it in engineering and astronautics. So what do satellites do? Well, we use satellites every day now for everything we do. You get TV, radio, guys have XM radio. I helped launch those satellites, direct TV satellites. I helped on those. I worked on your weather satellites. So when you go watch the news at night and they say, here's the weather picture from the satellite, I built those satellites, helped build them and design them. Lots of other things they do. The search and rescue, if you guys have boats or anything, or you go hiking and you hear people have these little personal beacons, we built those satellites. So those little beacons actually go tell the satellite up in the sky, and then the satellite beams it down to Earth so that somebody can come rescue you. So satellites do a lot of things. You know, you can spread data around the world, going from coast to coast around the world. It's incredible what you can do now. When I was a kid, you couldn't do any of this stuff. Okay. So, sorry. So the picture on the left is one of the first satellites we ever put, commercial satellites we ever put in space. And you can see it's pretty teeny. You got the guys, those two guys standing next to it. That was the first commercial satellite we did. We put it up in 1963, and it was used to broadcast the Olympics. So for the first time, the Olympics were in Japan, and people in America could watch it in real time. Before that, you know, they had delay, and you know, you had to watch it later in the time slot. They tape it and then send it back to America. But now we can watch it in real time. And so that was one of the first ones, and you can see it's pretty teeny. It's not even as big as those two guys there. But now they've gotten bigger and bigger. So you can see the one all the way on the left. That's not even the biggest satellite we build, but you can see it's pretty big. Those are real people next to it, putting it together. So I've worked on all these kind of satellites. And then just here's sort of a survey. I'm not going to go over all these, but satellites come in all different sizes and shapes. They've started, the first ones were the Russians built them in 57. And since then we've been working on them. They come in different shapes and sizes, lots of different capabilities, communications, weather, all sorts of different things they can do. You know, they take pictures now. We put up cameras and stuff. Of course, now you get all your, like when you do the Google Maps and stuff like that, some of that comes from satellite photos they built and stuff like that. So there's lots of different kinds of satellites. They're built by companies all over the world. We're not the only ones that build them. Europeans build a lot of them, and they're used for commercial and military purposes. So you can see a lot of them here. I worked on these ones on the bottom here. So this group I'm circling now, I built all these kind of satellites. This one right here is GOES. That's one of my favorite ones I ever worked on. I spent 12 years on it, worked from end to end. I'm really proud of that. Those weather satellites, they're pretty complicated, and it was fun. Here's interplanetary satellites. So, I mean, everybody's watching the stuff like the Mars rover. You can see there's one of the Mars rovers there. These, again, come in all different shapes and sizes, and they're doing scientific missions. So they have a lot of other different capabilities. They actually can launch probes. They have like little robots like you're seeing now that are pretty cool. They go meet up with asteroids and comets and collect samples of data and send information back, as well as just take pictures and signals and things like that. The early ones, the Mariners and stuff like that, really were just beaming through the planet, beaming through the solar system, taking pictures and beaming back signals about what they found. So here's a blow up of what a satellite looks like. There's two major parts to a satellite. There's the bus, and that's primarily what I've worked on. And then there's the payload. So the bus is the thing that allows you the satellite to operate and travel out in space. And the payload is the reason you're putting the satellite out in space. So that's your communications payload. So your relay or your direct TV transponders or your cameras you put on to take pictures of the Earth, things like that. And it comprises of a lot of different subsystems. So it takes, you know, I want to say 300 or 400 people to build one of these things, at least. And it takes a couple of years. I think the fastest we ever done was we got down, they were a lot simpler, about 30 years ago. So we could build and launch a satellite in about 18 months, but they've gotten much more complex now. And it usually takes at a minimum of 2 years to put one of these together because they're pretty much custom built. We have a lot of common parts, but everybody wants something different in their satellites, different kinds of things they're trying to do with them. So we have a common parts but we have to build custom stuff for them. And so, but we got down pretty, you can get 2 years, 3 years. One of the fun things I've gotten to do is work with a lot of launch vehicles. So there's a lot of different rockets we fly from around the world. And that's one of the good things of my job. I got to travel a bunch. Traveling does get old, but some parts of it are fun. And I had to work with a lot of these different rockets. When we buy a satellite, so we build the satellite, somebody else builds the rocket, and our customers will come and help them. We help them choose what rocket will best fit what they want to do. So all these rockets have different capabilities, and we figure out, given our satellite and what their capabilities, how they can get most out of it. Of course, the commercial guys, they're all making money on this stuff. So they want to get the longest life they can out of the satellite. And that's some of the analysis we do when we figure out what's the best combination of what launch vehicle, and then we'll work with the launch vehicle folks to figure out where they're going to put us in space and how we get there. So what's different about the space industry? So unlike your car, you can't, once we put a satellite out in space, you can't replace it. So most of my satellites are about 20,000 miles above the Earth. So the satellites you know about, like the space station, all the little other satellites you may know about, most of them are about 200 miles above the Earth. But the geo satellites, the ones we build, go 20,000 miles away. And once they're up there, you can't get them back, and you can't send people up there to repair them. So we spend a lot of time working to make sure that they're safe for, they operate for 15 or 20 years. Our satellites have operated for even longer than that. But usually we plan for at least 15 years. And we need to make sure they're safe and they work. So we spend a lot of time analysis, and then the components. So that means some of the components have to survive out in space. Space is a very difficult environment to work in. Down on the ground here, we're protected from a lot of radiation, but out in space, there's a lot more radiation, and there's not the atmosphere there to protect them. So they're subjected to a lot of things from the sun that would make them destroyed. So we have to build, so you can't necessarily use the electronics like you use at home. They have to be specially designed to work out in space and survive 15 years out in space. And then we have to put a lot of extra capabilities on board. So that's one of the nice things with computers. We made the satellites really smart. So they can kind of repair themselves autonomously. So we build software on board that detects if a unit goes bad, and we put a redundant unit on board, and then we can switch to that unit, and the satellite will do that automatically. Or if you don't want it to do it automatically, it'll at least shut down the bad unit and tell you what's going on, and then you can control it from the ground and tell it what to do. So it means a lot of work. We have to develop we're always working at very advanced technology. So some of the technology we develop in space eventually becomes technology we use on the ground, including things like disposable diapers. That was developed for NASA. You probably know this story, but when they first put astronauts in capsules, and then they didn't think about it because the guy was only supposed to be out in orbit for 15 minutes, and then he got stuck on the rocket for 6 hours before they could launch him. And they hadn't planned for having him to go to the bathroom. So that's why they came up with disposable diapers. So there's a lot of things you don't think about initially that you figure out. But yeah, it's very complicated. We're always working at advanced technologies. I'm still working advanced technologies. It goes faster than I can keep up with, but it's cool. And it always keeps the opportunity for learning more and doing different things and learning new things. So in 40 years, I've never been bored. I'll tell you that. I love what I do. And like I said, I've got to do a lot of different things. And of course, I get to work with, I said it takes like 300 people or more to build a satellite. So I usually work with a large team of people. There's a bunch of us. We work together closely. I worked on the same satellite for 12 years. So, and that was done 10 years ago. We still meet together and get together for lunch and stuff like that. So I work with a lot of smart people. It's great. and you learn a lot of things from them because they have different ways of thinking, and you always learn from other people and learn a different perspective of how to solve problems. It's great. So like I said, satellites can usually take at least 3 years. If you're doing something really brand new and crazy and different, it can take longer than that. God, they're trying to build a replacement for the Hubble telescope, and they've been working on that more than 10 years. Of course, there's other reasons why that takes longer than it should, but typically in our business, 3 years is a good one. If we're developing some brand new capabilities they've never done before, or some technology we've got that we want to use in a different way, it can take 4 or 5 years because what we do is a lot of advanced work on something we've never done before. If we're building something we've built pretty similar, then that's a 3-year kind of thing, because it's taking parts that you already got and you know how to put them together, and it's sort of similar to what we've done before. But I've worked on a lot of things where we've never done this stuff before, and you're trying to invent new ways to do it. So that takes you a lot longer. So it can take up to 5 to 10 years. But in that place, we started the concept development. I've done all this stuff. It's great. I've gotten to work through the end-to-end of the whole life cycle of the program. And that, in fact, GOES is the only one I did that. I actually worked on the proposal, which we won from the government, and then was there until we launched the last satellite and put it out in space. Usually you work parts of a program and then go off to another program, and then you come back, or you work at the end of a program. So I've done all of that. I've worked at the beginning. I've worked only at the end. I've worked in the middle. It's neat. You get exposed to a lot of different things. After you write all these on paper, how you're going to build it, and then you got to design it, and then you actually get to really starting on the design. And as you get into taking this thing you wrote on paper, you do a detailed analysis, and you get more down in the design, and you find out things don't always work as smoothly. Eventually you get to start to build things and put it together and test it. And so that's where I'm in the middle of it now. We're actually I'm at this assembly integration and test right now, doing unit and subsystem level stuff. We're building the different electronics right now, testing the boards, put them together as a box, and then that box gets put together with other boxes. It's really interesting. And I've written test procedures to make sure these things work right. I don't actually build electronics or design electronics. Other people do that, but I do a lot of overall concept analysis of how to fly a spacecraft, how to operate them. It takes a lot of smart people to do all this stuff. Eventually, we have to also develop all the procedures to run the satellite and do reviews. And then we actually spend a lot of time rehearsing. So you've probably heard about that. You've seen it in some of the movies. We actually simulate the whole, like it takes us 3 weeks or a month to put a satellite out in space and get it ready. And we'll spend time simulating that whole process. We'll try to scrunch it down into a couple of weeks, but we'll rehearse the whole thing, and we'll spend 24 hours a day just sitting there running all the procedures, pretending, we're doing what we're doing. We build simulators to do that. We have really high fidelity simulators that act like a satellite. So we get really ready and get to go. And then I get to participate at the launch and actually operating them out in space. And that process, like I said, it takes us about a month to get a satellite out there and ready to go. Sometimes they take longer. Some of the work for NASA and some of the science stuff, they like to spend a couple more months testing a satellite. Some of the commercial guys, though, they want to make money off these things. They want to get them operating right away, so they don't spend. We prove on the ground that all these things will do what they say they do. So the point is just getting them up and running and making sure we haven't broken anything in that process. And I usually let you guys talk, but I guess we'll wait till afterwards. I'm not used to talking this without you guys interrupting me, but I guess we'll wait till afterwards. So this is what a mission control center looks like. This is really a fancy dancy one. We build them a lot simpler, but it is a bunch of computers in a room with screens. Sometimes you have screens up in the front of the room. We usually don't at Boeing. It's more fancy for the government likes to do this stuff, because you're usually too busy watching what you're paying attention to. But you have a room like this with, when we're really busy, we got like 20 or 30 people on console at the same time. When we're really busy, a lot of times it's down to 3 or 4 people when there's not a lot of going on. But we run 24 hours a day when we're doing this stuff, so it takes 3 shifts of people. So if I need 10 people a shift, I got to have like a team of 40 or 50 people running in and out of there. And we do all that planning. I've done all that planning to figure out who's got to be where, when, and why at what time of day. So I actually build a 24-hour schedule that goes on for a month. And I got tools to help me do it, and who's got to be where, when, and what procedures we're going to run and what we're going to do and all that stuff. But this is the kind of room we be in. And, you know, when you're doing this stuff, it's pretty exciting at times. It's pretty nerve wracking at times. And you, again, you know, the satellite's 20,000 miles away. You're actually got a delay of about a half a second between signals coming back. You know, Mars is what is it, 8 minutes or something like that, or half an hour before the signals get back. So that can be nerve wracking when you send something and you're waiting for something to happen and you got to wait for your response. This is a picture of, and it's kind of old, but you know, this is what it looks like above Earth right now. And it's getting worse because some companies are putting a lot more satellites. I know Elon Musk is putting 1,000 satellites in orbit. He wants to put 3,000 more satellites in orbit. This is before that, but it's a pretty crowded space up there. And most of these are the low Earth. If you went to scale, you wouldn't see the ones in geo, they'd be off the picture. Because if you wanted to see the ones out in geo that I work on, the Earth would be a teeny little ball, like say the size of a marble on this picture. And there'd be a lot of space there, but yeah, there's a lot of satellites out there. It does cause a problem now. I actually last week, right? You guys saw that the Chinese had launched the rocket and they didn't properly make sure it got disposed properly. So it coming through the atmosphere and they didn't know where it was going to land. We normally plan for those kind of things. So when we put like, well, you've seen the Falcon, right? Those guys make those things re-enter and they control them with rockets. So they come back to Earth and they land on the ground or on a ship out in sea. Otherwise, we'll do stuff like the rocket will put the satellite out in space and separate from the satellite. And then the rocket will fire its engines so that it'll come back into the Earth and destroy itself. But we'll plan that so that it comes back into and lands over the ocean, not so it's going to land over California or something like that. The Chinese aren't so good about that, as we saw last week, but we're very careful to plan for that. So we're trying to be more careful about space, but it does cause, and it causes problems when we launch rockets. So when we're sitting there on the launch pad and we're trying to launch, there's guys watching for where things are coming. And sometimes the rocket will go up and you actually got to worry about, we got to delay launching for like 5 minutes because we're going to hit something if we go up at that certain time. So we'll get a warning from the Air Force, usually monitors that and supports us. They're online with them. And they'll say, oh, you can't launch in the next 5 minutes because the possibility you'll hit somebody. So this kind of illustrates what we do. This path here shows the satellite coming off the Earth. It puts it in an orbit. It's like this pink orbit here. We call it an elliptical orbit. It's not the final orbit you're going to be. And that's one of the things I plan is what's the best elliptical orbit I can put this in and then get the burns, because eventually I want it to be in this green orbit here. That's where it's supposed to be operating from. And it takes usually 5 or 6 maneuvers. You can see there's a symbolic rocket firing, satellite firing its rocket engine. I plan all those burns and I execute them. And it takes 5 or 6 of them to get from this pink elliptical orbit to this green circular orbit above the Earth. And what we have to do as part of that is we have to get ground stations all over the world. So we need tracking stations. You've seen those guys with big antennas. There's one actually not too far from here in the valley and out just past the valley in Fillmore, California. But they're all over the world, and we rent them. They're out for rent, so we'll go rent them. The government has some of them too, spread around the world, so we'll use them. And of course, I'm sitting here in California, so we have to get all the landlines and communications set up to be able to transmit through those antennas to talk to the satellite out in space, and to make those antennas track them. So we have to create all sorts of files that we automatically track the satellite. It's pretty interesting stuff. It takes a while to prepare. And of course, we have to get very high-speed data lines to do this between us and all these countries around the world. All right, so what does a satellite look like? So you're wondering, how can I put this big, huge satellite, which what you're seeing here on the right, how does it fit inside a rocket? So that's one of the things we plan for when we design a rocket, a satellite, is that actually we have to make sure we can fold it up and squeeze it so it sits inside a rocket. So here you see on the left side, the satellite all buttoned up and sitting inside a fairing of a satellite. So the cone of the rocket is this kind of grayish area, and this is like a cutaway, and you can see this satellite all buttoned up in here, and eventually it's going to look like this guy here on the right. It's going to be all exploded. There's this solar array put out. So here's the solar array I'm circling. It's kind of, you see like the single blue panel, but it's actually folded up and stacked. And we have these bolts that we have to fire and get rid of the bolts. And then it expands out and you get this big solar wing that you can see on the right side here. And yeah, so here's where I've got a really cool video. So the video I'm going to show you, let me bring it up real quick. It's so like I said, it takes us like 3 weeks to get the satellite fully deployed and up and running. This video takes about, I don't know, was it 30 seconds to run of what we take 3 or 4 weeks to do. But you'll see that the satellite, this is after the satellite's separated, and you'll see it start moving around and doing a lot of things. And I'll try to talk to it as we go. But yeah, this is really 3 weeks of stuff happening in 30 seconds. Give me a second here. Okay. So let me start the video. So the satellite's separated and it's spinning. And this is one of the things we do. We actually purposely spin that because it makes it easy to control. And so first it spins around one axis and then we just moved it around. So it's spinning around the other. And there you can see the rocket engine firing, that little flame. So now we're on orbit. We deploy the antennas. So there's the antennas coming out. And soon you'll see the solar wings start coming out. You see how fast they come out? It takes about 6 hours to get that all done, to get those solar wings out. About 2 or 3 hours per solar wing. And you have to perfectly plan it, and we have to be able to control the satellite. So now it's fully deployed, the antennas are out, the solar wings. So now there's the electric engines we have on it, which we use to control it once it's in orbit. And now we point it at the Earth. We deploy those last things are called radiators. And then it's all ready to do its job, whether it's to send you television signals or radio signals or do internet communications, or it's got telescopes or whatever to observe the Earth and bring the data back. And then it just sits up there. And then, of course, we have to plan for how to keep it up there because it doesn't naturally stay there. The gravitational force of the Earth, the sun and the moon push the satellite around. There's also the solar wind coming off the sun. It pushes the satellite around. So that means we have to regularly do things to maintain orbit. So we got to fire the rocket engines when it's to maintain its place in orbit. It usually happens once every other week or so. It depends on how you want to do it. So we got to plan all that, maintain its orbit. Otherwise it'll decay and not stay over where you want it to do. So I can send you another cool video that actually shows you the whole lifetime of the satellite and some of the cool stuff we do in the factory. Because of course, these are big, monstrous machines, and we have to have big, monstrous test machines to test the satellite. So last but not least, what should you plan to do if you want to work in a job like this? Of course, science and math is very important. This is not the kind of job you can come to if you haven't taken those courses in college. It's not like some other things which you can learn. You know, you basically have to go back to college and get it all over again. It's a lot of complicated stuff. And then it would be good to go to college that's strong in science and math and engineering. There's a lot of them. If you want a list of them at some point, I could send out a list. There's ones that are really good in the kinds of engineering. Most schools have some engineering and stuff, but there's a lot of really good ones, you know, UCLA and USC here in Southern California. They're all over the country, though. There's a lot of good ones. The important thing is to take advantage if you go to school like this. You can also, if you even want to start now in high school, our company brings in high school interns in the summer and gets them jobs. I don't believe we pay you as a high school intern, but you get to work for a month or two and you actually get assignments working here and learn stuff, get to work with engineers. Once you're in college, some of the schools we work with actually have co-op programs. So you can come and work at Boeing for 6 months, go to college for 6 months. Of course, it takes you a little longer to get your degree done, but you're getting paid while you're in college. And then once you get out, you've got a head start on it. You can come work at Boeing, and don't know if they have the co-op program that much anymore, but certainly during the summertime, you can come in and work as an intern. So if you're a college student, work as an intern, you get paid for that because now you actually got a college, you're working on your degree and working a program. So that's a lot of good things. Also, if you go to some of these schools, you can work with the graduate programs, do a lot of interesting engineering projects or science projects. You should take advantage of all that. There's also other things you should learn. You should learn good communication skills. It's important to be able to talk to people and explain to them what you know. Try to teach them, things and reading and writing, because eventually you're going to have to write down stuff you do. In fact, that's where I failed. I didn't write as much as I should have. And then, just to work, in college, you'll get to work on projects together. That's important. Important skill is how to work with others, work together. Everything we do is joint. There's very little you do by yourself. That's solely what you do by yourself. And again, like I told you, I've continually been learning my education. So I always continue my education. I always, I think I stopped going to USC about 3 years ago was the last time I took a course there. So I've never stopped my education. Anyway, I think that's what I had. And of course, why I love this. So I get to do cool things like this. I spent time down at the Cape. That was after we had just come down off that rocket. So I was up at the top of the rocket there, about 8 or 10 stories up. We were working on testing the rocket, making sure it was still okay, testing the rocket and the satellite. We have to ship it all the way from here to Florida. It actually goes on an airplane. We put it in a special container, and then you want to make sure it's still working after it's done all that. So we do a lot of testing down there. So I've been down there, and me and my buddies, we got to take a picture of ourselves when we came off it. So I think it's cool and a lot of fun, and I've been happy with what I do. So I guess I'll hand it over for the question period. I hope I didn't overtake my time, but Cheryl, you want to go ahead?
I have a question. What is your biggest challenge when you're building satellites?
The biggest challenge?
Usually, like, no,
It's,
like,
I don't know. It's always challenge. There's always challenges. You get through one phase, you think, oh, now I can relax, but maybe you relax for a month and then something else comes along and it's challenging. So a lot of times it becomes things go wrong and figuring out how to solve them and, keeping your head, you get nervous. I mean, these things are expensive. These satellites cost $300 million. So you think that you did something wrong and you broke something, that makes you nervous. I remember the first time I got to command a satellite, you're worried about, am I sending the right things? Do I break it? And in fact, the first time I got to test the satellite, we tried to send commands to it and the commands weren't going through. And I wait, did I hook up something and break something? And it turned out, no, that wasn't the problem. But yeah, it's stuff like that. You're building complicated equipment, and it's hard stuff. And you always worry about, am I doing the right thing? So I think that's kind of it. It's always challenging, which is good.
What are your longest work days? What are your most longer?
So, I normally work an 8 or 9 hour day. When we get into testing and stuff like that, or when I get into operating a satellite, I'll work a longer day then because sometimes you just don't leave. You got to get the stuff done. Like one time we had a test that should have taken us 3 or 4 hours to run, but we had trouble getting started and getting things hooked up and the signals weren't going through. And we had a lot of problems on the way. So a 3 or 4 hour test took us 8 or 9 or 10 hours. So stuff like that. Yeah. When I get into like flying the satellites, I'll easily work a 12-hour day or something like that, 10, 12-hour day. Especially on like launch days, the day we launch, those are really long days. They have to tell me to go home sometimes. We have to tell each other to go home. There's other people there that'll take over for you, and you're not the only person that can do this. So, but my normal work day is, 8 or 9 hours.
Oh.
Why is it that some satellites are like 200 miles from the Earth, and others are 20,000.
So it depends on what you're trying to do with the satellite. Um, all the scientific stuff, when they're trying to measure stuff at Earth, you want to be a lot closer. The instruments, the signals getting back and forth from 20,000 miles away have to be really strong signals. But like a camera, you want to be able to take high resolution pictures. You'd have to build a huge, huge camera if you're 20,000 miles away, but you can build a much smaller camera if you're 200 miles away. So it depends on what you're trying to do. Again, now if I want to do direct TV or XM radio or something, and I want to broadcast, cover the whole United States, I want to be farther away because then I can cover more area. So that's the different reasons you have for the different orbits. It's what you're trying to do and considerations like that.
Anyone else have a question they'd like to ask Mr. Birnbaum?
You know my dad?
I might.
Naveed Hussein.
Oh, I know Naveed. Yeah,
Ah,
Naveed's a great guy. He's a bigwig now.
he what?
He's a bigwig now.
Yeah, he's a senior vice president of
Yes.
Boeing.
I knew him when he was just a regular guy like me about 20 years ago. He was just another engineer like me, but he's moved up in the ranks. He's a good guy. I like your dad.
Thanks.
Anyone else have a question that you'd like to ask? We've got about 1 or 2 minutes left.
And by the way, that's one of the other things about this career is you can move as far up or as low down as you want to go. So I'm kind of in the middle level. I was, a little junior engineer when I first got here, and I've moved up to a middle level, and I'm happy where I'm at. I don't want to go higher. I could have if I wanted to, like your dad Naveed did. But that's a good thing about working in a place like this. You can go as far as you want to go or not want to go. You can work on what you want to work on. If you like doing one thing the whole career, I've known guys that did the same thing for 40 years and they love it. I like to do different things. So that's one of the nice things about doing something like this.
What is one of your favorite jobs that you worked on in Boeing? Because you worked on a couple.
Yeah, well, like I said, the Ghost program, I love that. That's where I learned a lot of different things. When I first did there, I was just the orbital guy doing orbital analysis, but then I got to learn how to test satellites and write test programs. I got to learn, that's where I started learning how to actually operate satellites and send commands to satellites. I learned about all the communication networks. So that was probably, the Ghost program was my favorite. And then the one I'm working on now, we call it P122. That's my second favorite.
How many satellites have you launched?
Something like 50, at least 50, I think. Yeah.
Wow.
All right, everyone. I think it is about 2:40. Mr. Birnbaum, you talked to Blue Streak. Thank you so much for being here with us today. There was lots of great information for us. Can we all undo those screens maybe and give him a little bit of soundless applause? Or thank you.
Thank you guys for listening.
All right, everyone. Have a good rest of your day. And again, thank you so much, Mr. Birnbaum, for being with us today for our CF Expo.
Thank you so much.
You bet.
Thank you so much.
It was fun.
Thank
I like
you.
talking about this stuff, so it's no problem.